In this lecture, we proved the Borsuk-Ulam theorem. This you can find on page 176 of Hatch's algebraic topology. So the theorem says that for every map f, so this is a continuous map from the sphere to the plane, there is a point x in the sphere where f of x is equal to f of minus x. So that is both x and the antipodal point, they map to the same point in Rn. So to prove this theorem, we will use this result which we proved in the last lecture, that if you have an odd map, this var phi from the sphere to sphere, then this map will have odd degree. So we are going to use this result. So step 1 is you construct this map phi of x and put it as f of x minus f of minus x. So this will be an odd map, as you can immediately see. So we need to show that this odd map is 0. So that is, this f of x will be equal to f of minus x. So we will go here if we are able to show that this phi of x is 0. So what we are going to do is we are going to prove by contradiction. We will assume that phi of x is not 0, and from here we will construct a map from Sn to Sn, but this map will have degree 0, so which will contradict this. So you have an odd map which should have odd degree, but we are assuming phi of x is not 0. This will give us a degree 0 map which contradicts that it is odd. So this assumption has to be incorrect because this leads to contradiction. So let us now show the proof. So proof by contradiction. Suppose phi of x is not 0, and we note that phi of x is odd. So by construction you can see it is odd. So then you can divide this phi of x by this. This is not 0, so you can divide it by its norm so that you can have Sn to Sn minus 1 map. So you have constructed this map Sn to Sn minus 1. Then you construct the restriction of the map. So from Sn you can always go to Sn minus 1, its equator. So you have this map Sn, we are breaking it to Sn minus 1, and we are saying this map Sn to Sn minus 1, we are going to go from Sn to Sn minus 1 and then this map. But this map here is null homotopic, so that is degree would be 0. So the restriction to equator is null homotopic precisely because this Sn minus 1 is boundary of a contractible space. Just like if you have sphere, you have S1 here, this map would be null homotopic because this S1 is the boundary of the hemisphere, and this hemisphere will contract to a point, and this is the S1. So again this is S1, but everything will contract to a point because this is just boundary of this hemisphere. So this map is degree 0, so you compose this like this, you have to multiply by 0, so this map will also be of degree 0. And that's what we wanted to show. So you have this, so we have a degree 0 map which contradicts that this is an odd mapping. So now we give 4 statements which are equivalent to each other, and all of these statements essentially say the same Borsuk-Ulam theorem. So we have proven this number 1, and we will show that all of them are equivalent. So let us first focus on 1 and 2. So 1 we have just proven, so that for every map f from Sn to Rn, there is a point x lying on the sphere such that f of x is equal to f of minus x. So both the point and the antipodal map to the same thing. So for every antipode preserving map, so this map f from Sn to Rn, so antipode preserving means that f of minus x is equal to minus f of x. So if there is an antipode preserving map, then there is some point on the sphere x such that f of x would be 0. So this is also a statement for Borsuk-Ulam. So let us see that 1 and 2 are equivalent. So first we will show 1 implies 2, and then we will show 2 implies 1. So we start with 1. So from 1 we have f of x is equal to f of minus x for some point x, and we are saying the map is antipode preserving. So that means f of minus x is equal to minus f of x. So we'll copy this right here. So now we just put it together. F of x is f of minus x, and then this comes right here. So then take this on this side, so you have 2 f of x is 0, which implies f of x is 0. So that is what we wanted to show. F of x is 0. So now in the opposite direction, 2 implies 1. So you start with 2. So you say you have a map G from Sn to Rn, and you set g of x is f of x minus f of minus x, precisely because this will be an antipode preserving map. So you can see g of minus x is equal to minus g of x. So this is antipode preserving map, and we are assuming 2 holds. That means there will be some g of x which is 0. So g of x is 0. So when you set this equal to 0, you obviously get f of x is equal to f of minus x, and that's what we wanted to show here in number 1. So now we will show that 2 implies 3 and 3 implies 2. So 3 is, there is no antipode preserving map phi from Sn to Sn minus 1. So there is no antipode preserving map. So first we will say that 2 implies 3. So you construct this map Sn to Sn minus 1. You have this map phi, and then you include this in Rn. So you compose these two, you have this map F. So F is phi composed with the inclusion map. So now we are starting with 2. So because we are starting with 2, so you have this map F Sn to Rn. F of x is 0. So f of x is 0, and we assume that phi is antipode preserving. So we have to show that phi is no antipode preserving. So we are going to assume that phi is antipode preserving, and that is going to lead to a contradiction. So this would imply immediately that there is some x for which phi of x is 0. Because f of x is 0, this map is simply an inclusion map. So if f of x is 0, so this phi has to be 0 on some x. Now this is a contradiction simply because phi of x actually lands in Sn minus 1, and this sphere does not have origin lying on it. So now we are going to apply this thing. 3 implies 2. So essentially this is a contrapositive. Not 2 would imply not 3. So not 2 means that this f of x is not 0, and not 3 would mean that you have an antipode preserving map. So we are going to recast contrapositive as contradiction. So we start with this not 2. So say f Sn to Rn be an antipode preserving with f of x not 0. So if f of x is not 0, you can also construct antipode preserving map from Sn to Sn minus 1. Simply divide f of x by norm of f of x. So this is an antipode preserving map, which is not 3. So essentially we are saying that if you assume 3 and you assume that f of x is not 0, you get a contradiction with 3. Or this is just simply this contrapositive. Not 2 implies not 3. So f of x not 0 implies antipode preserving, because 3 is no antipode preserving. So now we come to number 4. So number 4 says, so say you have covering of Sn by these n plus 1 sets, a1, a2 all the way to an plus 1. So these are closed sets. Then there is at least one ai which contains a pair of antipodal points. So this is the best possible. So for Sn, this is n plus 1. If we increase one more set, we can find a covering actually which will not contain antipodal points. So what I'm trying to say is, say you have S2 and then you cover it by a tetrahedron. So this is a S2, this is living inside tetrahedron. Then you radially project this tetrahedron onto it. So this tetrahedron has 4 faces. So you will have S2 covered by 4 sets, A1, A2, A3, A4, and none of them will have antipodal points. So for this statement to hold, then there is at least one ai containing a pair of antipodal points. We can cover S2 with A1, A2, A3. So this 2 and this 3, this n and this n plus 1. If you increase the cover, then obviously, just like in this case, you can find a covering which will not contain antipodal points. But if you have exactly or less than this n plus 1, then you will have something which will contain the antipodal points. So there is some AI which will contain the antipodal points. So let us start by showing this 4 is equivalent to this 1, 2, 3. So first we will show that 1 implies 4. 1 implies 4. So you take a cover of Sn by these sets A1 to An plus 1, and you have this map Sn to Rn, which is just given as this point x you feed in, and its first coordinate is the distance of this point x from set A1 all the way to x to An. So there are n coordinates here, Rn. So notice that we are not writing this An plus 1 in this thing here. So one says f of x is equal to f of minus x, but this distance function is always positive. So that means that if this holds, that means for some x you have x ai is equal to minus x ai. Now if any of these distances is 0, so this distance would be 0 for any set if x belongs to ai. So in that case both x and minus x would lie in ai. So if any of these coordinates is 0, so then both x and minus x would lie in that ai. Now in case none of the coordinates are 0, then you're still left with an plus 1. So none of the coordinates of f of x are 0, then x and minus x lie in an plus 1. So 1 implies 4. So you assume this, you will definitely have there is at least one ai which contains a pair of antipodal points. Now 4 implies 3. So for this we will just use this not 3 implies not 4, which is a contrapositive. So first you note that it is possible to cover Sn minus 1 with n plus 1 sets. So this is n minus 1. So for 4 to work we can have only one more. So if this was n minus 1, you have to have n sets, but we are saying n minus 1 you take n plus 1 sets, and none of these sets contain the antipodes. So this is easy to see in S2. So as S2 you have these 4 faces projecting onto it. So inscribe S2 in a tetrahedron. Tetrahedron is called a 3 simplex. So and radially project tetrahedron on the sphere. So then none of the 4 faces contain antipodal points. So same strategy is adopted for Sn minus 1. Inscribed it inside n simplex. So just like S2 is inscribed in a tetrahedron which is 3 simplex, here you have Sn minus 1, one more n simplex. So we get a cover of Sn minus 1 with these sets T1, T2 all the way to Tn plus 1, such that none of the Ti contains antipodes. So if you have a covering here that none of the sets contains antipodes, so you have a proper covering. So assume not 3, so that is there is an antipode preserving map, you will get not 4. So assume there is a continuous antipode preserving map, because 3 is that there is no antipode preserving. So you say there's an antipode preserving map f Sn to Sn minus 1, then you can take the cover of this, which is by these sets, take their inverse image, and then you will have these sets n plus 1 sets, which is given by f inverse of Ti. So these sets will cover Sn and none of them contain the antipode. So because they do not contain the antipode here, you take the inverse image, that will also not contain the antipode, and which is precisely not 4, because here we are saying at least one ai should contain the antipode, and here we have not 4. So assuming there is a continuous antipode preserving map gives us a not 4, which is that none of the sets in the cover will contain the antipode. So that's what we have. So we have proven 1 implies 4, and then we have proven that 4 implies 3. So 1, 2, 3, 4 are all equivalent to each other. So Borsuk-Ulam theorem is stated in any of these 4 forms.